Yep, I got it.
Okay, you got it. All right.
Hmm.
Cool. All right, so we're gonna go over some key concepts and then some applications. We kind of split it into three. We're gonna do some solving for unknown variables, and then some EOM and the energy method. And so all of these, you can find in your book. You can also, go look at Chegg, but you could just use this for some reference. So some key concepts. So what is vibration? Vibration is any motion that repeats itself after time interval, and it's also just the transfer of potential and kinetic energy. So we see this in everyday life: cars driving down the road, bridges, etc. Um, Good thing to know would be the difference between periodic motion and harmonic motion. Periodic, you can kind of think of the unit circle. So it's any motion that repeats itself at equal time intervals. So a time constant would be a good idea to a good thing to think about. Whereas harmonic motion is any motion where acceleration is proportional to displacement. So this is kind of this is where the whole phase angle comes from. Everybody kind of asks what phi means. And so it's when you have multiple degrees of freedom or multiple masses, each kind of doing their own thing. And so you have different vibrations, and you can have those different vibrations can also interact with each other and cause some issues. So harmonic motion would be something that we should all know as engineers. Hold on 1 second. So yeah, here's just a easy depiction of it. If you look at the dotted line, how the different waves um, are off by pi over 2, so that would be the phase angle. Good thing to know is the small angle assumption. We should all know that by now. So if the angle is small, which with all of these problems, unless explicitly stated in the problem, you can assume this. So obviously cosine theta or cosine of 0 is 1, and sine of 0 would be that. I'm sorry, so sine of that angle would be theta. And it's to linearize the nonlinear differential equation, so we can compare it to the characteristic equation. That's why we want to assume that. Um, Displacement is measured from the static equilibrium, which is the point where the mass is in static equilibrium or stationary. So, if we can just think of a mass on a spring, it would be before that initial force, or it's more of just that initial condition. Effective mass, spring constant, and damping constant. These are going to be what you're solving for most of the time. You should all have seen this in your homework. Just kind of remember, springs store potential energy. Dampers are used for energy dissipation. So energy is not conserved when you see a damper. And mass stores kinetic energy. Some other things that we should all know is free vibration versus forced vibration. So free vibration is, kind of just naturally, whereas a force vibration is given that initial force. So if you want to think about throwing a ball up in the air and letting it bounce on the ground, that would be force vibration versus just letting it sit there. Linear versus nonlinear vibration. So linear vibration is kind of we can use superposition, um, and it's more of an idealized case versus nonlinear. That's where the K equivalent kind of comes from when you combine all of that. Um, that's more of what reality is, but we don't really focus too much on that in this class. Um, we're going to go over to natural versus damped frequency. So natural frequency is just a vibration system um, that doesn't have a damper in it. That's all it is. Damped frequency, obviously, it's natural frequency with a damper. So undamped versus damped, it's kind of the same thing. You could think of undamped. when you think of natural frequency. Damped has a dampener. So the difference between damping constant and damping ratio, I've been asked that a lot. So your damping constant is that C value. It has to do with what kind of a damper you use versus the damping ratio, which kind of tells you if it's over damped, under damped, or critically damped. So under damped, we're going to have a lot of peaks and it's going to go gradually to zero. Over damped, it's going to go straight down. We're not going to see a lot of vibrations. We're not going to see a lot of peaks. It should just go straight down. Critically damped is kind of your most optimal case because, you know, you do see some frequencies and it's kind of the best of both worlds. You don't want a system that's too damped because you lose a lot of energy. So yeah, response times of the different damping conditions. This could be a good conceptual question that you might see. And it does come back later. So definitely this figure is definitely something that you guys should know. So why do we care about logarithmic decrepitment? It's a good way to measure frequencies and to measure that that damping ratio when you don't know what your damping constant is. So you can kind of work your way back by measuring the frequencies. So can we use that equation, the log decrement formula for an overdamped system? We can't because there's not two different peaks. If you look at this, get my mouse over here. If you look at this line right here, it just heads straight down to zero. So if you look at that equation where you have two different amplitudes, you have an X1, but you don't have an X2. So you can't use that equation for an overdamped system. So when zeta is over 1. So some things to remember, kind of, you know, I just jotted down some things that you know, made my life a little bit easier when I took this class. So disregard gravity unless it's acting as a restoring force. This is a big one. Definitely make your life a little bit easier. We're going to explain this a little bit more. I'm going to look at the chat. Okay. Yeah, we're going to go back to that because we got a whole bunch of questions about the restoring force. Natural frequency in terms of gravity. This is a good derivation to know, especially with the vertical motion and pendulums, I believe. It just kind of goes over the how we can relate natural frequency to gravity and just the static displacement. When should we use the equation of motion approach versus the energy method? This, if I would have known this when I took this class, it would have made my life a lot easier. Because, you know, I do a lot of homework, and unless it's stated in the problem that you know, use the energy method, you don't really know until you kind of, you know, use some trial and error there. But EOM, or equations of motion, using those, it's very practical for 1 degree of freedom problems. So that's you know, the mass connected by a spring and a damper. Energy method is great for the more complex problems when you have, you know, multiple masses and multiple moving parts. But if you see a damper, they dissipate energy and energy is not conserved. Therefore, you cannot use the energy method. And we'll see an example of this later. So characteristic equation versus the standard characteristic equation. So this is what we're going to be trying to solve for. And then we're going to be comparing it against this one. So the roots of the characteristic equation, are these the same equation? Yes, they are. What I would do, so my advice would be to, you know, if you go into the formula sheet for like the different cases, they have, I don't know if it's on the formula sheet actually. Hold on. Yeah, I don't think so. So, you know, people were asking me like, you know, can we just memorize the equation for the different damping conditions, you know, if it's under damped, critically damped, over damped. I would just go straight to these two equations because, you know, all you got to do is plug a number in, you know. And obviously, you know, if this comes out to be negative, you got a complex number. You didn't use them at all in the homework. Did they not use the roots, Michael?
Um, so with the roots, I think she might just use those in proofs, because I think how they'll determine if it is damped is by the damping ratio, and
Okay.
then from there they'll just go straight to the solutions in the formula sheet.
Okay. So I guess you guys can hold off on this. I mean, you're gonna need to know it at least next test. He hadn't had any problems with roots, I think. Okay. All right. All right. Yeah, I saw it on her notes. Okay. Cool. So yeah, you know, if you guys haven't had any homework problems on it, I apologize. Yeah, just you can kind of disregard that. Um, but yeah, you know, these are the roots of the characteristic equation, and yeah, they are the same. I'm just trying to show you this because um, it shows that the comparison is correct, I guess. Last homework question and okay. Also, this is just another good thing to remember. For critically damped systems, your zeta is going to be 1. So C equals C crit. So process for modeling using differential equations. This is kind of the bulk of this exam. So the first thing you should think of is, you know, what coordinate system am I using? You know, this takes us all back to dynamics, you know, sophomore year. Am I using Cartesian, spherical, polar? We've only done Cartesian, I believe. But you know, it's just some, you know, which way is up, which way is down. What is my positive direction? What is my negative direction? Where are my masses naturally or forcefully trying to go? Is there initial force, or is my mass block going to be falling because of gravity? These are the things that, you know, we should all think about. But mainly, what I do with, especially with dynamics problems, is, you know, I just try to think about it in my head and ask myself what would happen in reality. What would happen if I push that block against against a spring? The spring is going to want to push back. So that's the first thing that you should do is just kind of try to visualize it in your head. Next, draw a free body diagram of each moving part, mass, like, you know, for example, the masses, as well as I like to do a whole bunch of the little ones of, you know, if I have a whole bunch of different masses moving around and they have a whole bunch of forces, I like to draw those separately, but then also one of the bigger picture, and I label all my forces out. Step 3, we're going to apply Newton's second law. So are there any moments acting on the system, or can I get away with just doing a force equilibrium? You know, is it translational motion or is it rotational motion? Am I using, you know, angular acceleration, or am I just using, you know, just linear? Which moment of inertia should I use? You know, are we going to use the mass moment of inertia, or are we going to use the polar moment? Next, we're going to input the appropriate spring and damper forces, and we're going to set it equal to 0 and go from there. I just kind of wanted to go over this a little bit more. It's something that kind of confused me in the very beginning. So the reason that we set up this block like this, yx1, it's x1 minus x2. It's because if you see this force right here, that is your initial condition, right? So this block is going to have a force on it. It's going to move this block first. So my displacement, my x1, is going to be greater than my x2, right? So that's why we have, and it's also going to be, so the blocks like this, right? My spring and my dampener are pushing it this way. The force of my spring and dampener have to do with my displacement. And my displacement would be positive in the way that this problem is set up. That's why we want to do it that way. But it's the force the force comes out to be positive, but it's going in a negative direction. So it's just kind of, these are the sort of problems that you have to do a whole bunch. You just have to go through like the first step to try to make sure that your free body diagrams are correct. But something that I did was, you got a whole bunch of examples in your book. You don't have to do the whole problem. Just get the free body diagram set up if you're having issues with it, and just trying to make sure that that's correct and do some practice with that. Yeah, as long as it's consistent. Yeah, I'm going to try to post the slides. All right, restoring force, something that everybody's been waiting for. Michael, you want to take this one?
I'll take over, and I'm going to see if I can request remote control.
Oh, I like that. That's new. Cool.
So I could. Okay, yeah, cool. All right. So when talking about restoring force, basically from physics, restoring force is just any force that tries to bring the system back into equilibrium. And so we'll see in cases where we can ignore it, like in the cases of a hanging mass, because gravity will be pushing you away from the static equilibrium position, like so. Don't have control. Oh.
Am I screwing you up?
I think we're good.
All right.
Okay, yeah, we're good. All right. So here. So yeah, this is the Y. Gravity moves mass away from the static equilibrium position instead of towards it. And now if you wanted to see the math behind it, you could start with your static equilibrium equation where the force of the spring equals kx, and you know that you have weight down, spring up, so weight equals the force of the spring. And then we bring it into our equation of motion. Sum of the forces equals mx double dot. You'll have your force balance, weight minus spring force, equals mx double dot. You know that the spring displacement is now whatever it was plus the delta, the dst is deflection. That's how much the spring changes in length. So you know the new deflection is that, and then your weights will cancel out, and that's in short how we can say non-restoring forces get ignored in the equation, because they'll all cancel out in some way like this. But now if we look at a case where we can't ignore it, we have pendulums. And why is that? Because the gravity will always bring the pendulum back to static equilibrium position. It doesn't matter how you displace it. If you move it from equilibrium, there is some force of gravity that is pulling it back towards equilibrium.
All right, back to me. This is something that was kind of brought to my attention by one of you. So I believe it was problem 38 in your homework. That just the wording of it is just something that we should all just pay really, really close attention to. So here it asks, determine the natural frequency of the damped system, right? Does anyone know what that is asking? Is that natural frequency, or is that damped natural frequency?
Isn't that damped natural frequency?
It's actually natural frequency. So this one, 40, says the natural frequency of damped oscillation. That would be damped natural frequency, because the system is damped. It's asking for the natural frequency. It's just really weird wording. Natural frequency. Okay, yeah, it's just, it's something it's a bad question, but it's something that I thought, I should probably just bring that to everybody's attention. When you see the natural frequency of the damp system, just go straight to omega n. But if it says the natural frequency of damped oscillation, it's omega d. And I actually, now that I think about it, this might work out to not having any. Was this damped? It was, yeah, it was damped. Yeah. So yeah, when you see this natural frequency of the damped system versus natural frequency of damped oscillation, just kind of remember that. So oscillations, they both oscillate, yes. But honestly though, she'll make it pretty clear what she wants. You're not going to get something like this, but it's something that I wanted to bring to everybody's attention. Her tests are always very fair. You're not gonna be wondering what you're asking for or what she's asking for. So now we're gonna get into some applications. This is the same exact problem that you just saw. This is 240 in your book. So a vibrating system has the following constants. Mass is 17.5 kilograms. Your spring constant is 70 newtons per centimeter, and our damping constant is 0.7 newtons per centimeter per second. So we're going to determine the damping factor. We're going to determine the natural frequency of damped oscillation. We're going to also calculate the logarithmic decrepit and the ratio of any two consecutive amplitudes. So these are our knowns. This is what we're solving for. So step one, we're just going to convert. We want these in meters. We don't want them in centimeters, because when it comes to our frequencies, and when we solve for omega n and omega d, we're using radians per second, which requires, if we're going to be solving equations going 2 radians per second, we're going to need meters. We can't use centimeters. Step two, we're going to find and solve an expression for zeta. We know that zeta equals the damping constant over C crit, and we also know that C crit is 2 times the square root of K times M. So we can combine those and say that zeta is equal to the damping constant over 2 times the square root of Km. We're going to plug our numbers in and we get a zeta of 0.1. I'm looking at the chat real quick. Yeah. So yeah, like I said, it's just a really bad question. But you shouldn't worry about anything like that on the test. You'll know what she's asking. Step 3, find and solve an expression for omega d, your damped natural frequency. So it'd be your damped natural frequency is omega n. Natural frequency of the damped system, that's omega n. But yeah, bottom is 2 square root Km. Yep. So our omega n is square root of K over M. We know that from the formula sheet. So we can plug that into this expression here. Or, we could also solve, for a natural frequency and then find a value for that and then plug that into this equation. They both work. We get 19.9 rads per second. And you guys should definitely know how to switch between frequencies, switch between radians per second and hertz. You just divide by 2 pi. You get 3.167 hertz. I don't believe back when I took this class that she asked something like this, but you never know. It's one of those questions. It could be part E, and you don't want to be caught on something like that. Something that's you can memorize like the back of your hand. So step 4, we're going to find and solve an expression for delta, or the logarithmic decrepit. We know this equation, 2 pi zeta over the square root of 1 minus zeta squared. Plug in our values, we get a value of 0.6315. Step 5, find and solve an expression for the amplitudes. So if you go back here to the question, it's the ratio of any two consecutive amplitudes. So that's what we're solving for. Hate writing these symbols, kills my OCD. Yeah, I know. Sorry, it's not the prettiest. So yeah, we have, if we look at our formula sheet, we're gonna just use this equation right here. It's delta equals natural log of x1 over x2, because we have that. We already have delta. Why make our lives harder? Plug that in. Take the what is it? E exponent on both sides, and we get a value of 1.88. So this means that my first amplitude is going to be 1.88 times my second amplitude. Scribble randomly. Yeah. Can I slow down a little bit? Yeah. I can go back if you guys are copying this down. And I will be, I'll try to post these, and we are recording. Can I go back? And I should have, you guys should be able to unmute yourself. So if you have any questions, feel free to butt in at any time. Let me know when I can go ahead. Okay, cool. Oh, that's actually a good idea. Michael, do you want to actually?
Yep, I'm on it.
Yeah, that file button right there. See if that works. Okay. Next question, we're going to do 243, another good example from our textbook. Yeah, there it is. We'll do the same thing. So I know that the chat might get a little crazy. We'll post the PowerPoint at the very end as well in the chat, and we'll also post it on web courses. And we're also posting the recording of this. So we're going to be doing good. Something else that I would do, this is kind of off topic, but you shouldn't have the formula sheet printed out in front of you. I think that she said that yesterday. But something that I would do when I'm studying for these and I'm doing a whole bunch of example problems is I would print it out and then go through whatever questions I'm working on and whatever examples I'm trying to go through. If I don't have an equation there, I put it on the back. So I have it in front of me, and then before the test, I look over the equations that I don't have on the formula sheet, and I try to do my best to either get familiar with them or hopefully I can memorize them. But you don't want little stupid ratios get in between you having an A or a B. So I definitely use that approach. For example, I'm gonna go into it, but the delta versus zeta expression, if you solve it for zeta, that would be something good to remember. What's up, Alexander?
Hey, Andrew, real quick. I've been thinking a lot about what Professor said about how we can't print out the formula sheet, and she said did she say we are going to be able to access it during the exam?
Oh, of course. Yeah. That's what it's for. It's
okay.
Yeah, you shouldn't have a problem with that. And something that I'm kind of worried that that I might bring up with her, we're going to try to make sure it works. Just triple check it, because I've gotten into tests sometimes with Zoom University.
Yeah.
Where you go to download the PDF of the formula sheet and the lockdown browser doesn't let you do it.
Yeah.
So yeah, we're gonna make sure that works.
Okay.
but it's just kind of, it has to do with like the security and, academic integrity.
Yeah,
It's
course.
just something, it's one less thing that we have to think about. So
Right.
that's why she doesn't want you guys to print it out.
I figured. It's just I've never encountered a situation where we use Lockdown Browser and have to access another file as
Yeah.
well as the test.
Yeah, you should be able to.
It,
I
it won't
haven't- I
even be a
haven't been-
separate file. It'll just, you'll open up the test and it'll be like a question box, but instead of a question, they call it like a spacer, and it will just be there.
Oh, really? Oh, okay, good.
Yeah.
Okay.
And there shouldn't be a whole lot of scrolling either. These questions, you'll have 3 to 5 questions. Formula sheets up at the top. You'll have 3 to 5 questions, and you shouldn't have to scroll. If you have like a multiple choice test and you're on question 30 and you need that formula sheet all the way up at the top, it's a pain to go all the way back up there and getting it. But we're only, it's 3 to 5 questions, something like that, and it shouldn't be that big of a deal.
Okay, makes sense. Thanks, guys. I appreciate it.
Yeah, no worries. How would you access a PDF scan when we're scanning the document?
There'll be a separate assignment for submission.
Yes. Yeah, we had a lot of issues with that last semester, so I think we're kind of giving up on it. Like Michael said, there should be a separate submission. Yeah. Lit.
Quick question too. Is it gonna be like a fill in the blank kind of response in the actual test? And then so we put in our answers that we finally get and then we upload after?
I don't believe so. I
It's
think
just like the standard, like upload your PDF like normal.
yes.
So there will be, at least when I took it, there was an option to do it. But what really counts is your scratch work. So if you don't get to it in time, but you still submit a PDF, you're probably fine.
Okay, thanks.
What's the chances of us getting a circuit question?
Slim.
Yeah, slim. So that it'll come up later though. I'm not saying you should know it. It does cut like the DC motor problem and the circuit problem, they will come back. Yeah, they're like ghosts. I really want to be done with circuits. Yeah, don't we all? Yeah, I mean, she changes her tests every year though, and those circuit problems, they're on the formula sheet. She's got the circuit equations on there, so she hasn't put them on the past 2 tests, but I'm pretty sure I heard something about some 3 semesters ago. We haven't seen the test, so I can't tell you. I explicitly don't study circuit problems. Just focus on the concepts of using the equations of motion, and it's kind of the same. It's the same concept with the circuit problem. It's instead of motion, it's electricity. We've all taken electrical, correct?
Yes.
Yeah. Okay. So I mean, just brush up on it a little bit. I mean, it shouldn't take you that long. Just because the probability of us getting a circuit problem is low doesn't mean it's 0. So, you don't want to be caught outside. Okay. I think Michael blinked 3 times. All right. So we're going to keep going. If that's all right with you guys. Like I said, if you have any questions, it's hard for me to kind of look at the chat, but either raise your hand or unmute yourself. So question 43, a spring mass system with viscous damping is displaced from the equilibrium position and released. If the amplitude diminished by 5% each cycle, what fraction of the critical damping does the system have? So this is one of those questions where it's kind of ambiguous as to what it's asking. So if you don't really know what the amplitude diminished by 5% each cycle, so if you just like see those equations on the formula sheet and you don't know what they actually mean, this is where they get you. This is an easy question that a lot of people will get wrong. So our knowns, the only thing that we know so far is the amplitude diminished 5% each cycle. So that means that if our second amplitude, so our x2, is 5% lower than x1, our first amplitude, then x2 is 95% of x1, or x2 equals 0.95 times x1. This is something that we should know. This could very well be a problem. This, because we'll have probably 2 easier questions and then 2 longer problems, and this would be one of the easier ones that can trip people up. But if you do know your stuff, it's super easy. So step 2, what are we solving for? It says, what fraction of the critical damping does the system have? When I see fraction and critical damping, first thing my head thinks of is zeta. That's the ratio. Ratio means fraction. So zeta equals C over C cret. Step 3, find relation between amplitudes and zeta, right? So we know this, and we know this. That's the thing with these questions, is you got to write down what you know, what you're solving for, and what equations you have in your arsenal to be able to get you from point A to point B. A lot of times you won't be able to get, from point A to point B without doing, 2 little calculations in the middle. So it's very important to be able to write down what you know and what we're trying to go, where we're trying to go, what we're trying to solve for. Step 3, find a relation between amplitudes and zeta. So we know that delta, or logarithmic decrepitment, I'm just going to call it delta from now on. I hate saying that word. We know that that's equal to 2 pi zeta over the square root of 1 minus zeta squared. We also know that it's also equal to the natural log of the ratios, the amplitude ratios. So we're going to solve that out. We're going to solve the delta equation, the delta relation in terms of zeta out, and we're going to have an expression for zeta. We're also going to do the same thing over here. We're going to plug in our known, just substitute our x2 in, and we're going to come out with our delta equaling 0.05129. You mean, technically, you could also set these equal to each other. You'll get the same thing. This is just the way that I did it out of the gate. But with that square root in the denominator, it becomes a little tricky. But this equation right here, I'll go over the derivation in a second, but definitely be familiar with this. It'll save you a lot of time, because going from here to here, it's just like there's so many ways you could screw up the littlest, tiniest thing, and your whole answer is wrong. And I don't want that to happen. So now that we have our delta and we have our equation for zeta, we plug our delta in, and we get a zeta of 0.00816. So, or damping ratio, zeta, same thing. Like I said, or you can just set them equally to each other to find our zeta. But I don't recommend doing it that way. It gets a little tricky. So yeah, like I said, the dampening ratio derivation. Somebody came to my office hours. They had a question about this. Definitely something that we should know. Do you have to show? If we use this right here, I memorized it. Yeah, I just memorized it when I took the class. I actually recommend you guys memorize it. So, I mean, it makes your life a hell of a lot easier. It did as well. I didn't have any problems. Yeah. So first thing we're going to do, square both sides. I hate when I go to look at Chegg and I see stuff like this and they have no like derivations, no like, sometimes I want to see it kind of worked out. So the first thing we're going to do is we're going to take the square root of both, we're going to square both sides, get rid of that square root in the denominator. Then we're going to move the denominator over and distribute, right? So we're going to try to get this zeta over here. We're going to move it on the right side. So get zeta on one side and isolate. So 4 pi squared zeta squared plus delta squared zeta squared equals delta squared. We're gonna take that zeta squared out, and we're going to divide by 4 pi squared plus delta squared. Take the square root of all that, get rid of this square, and we're left with delta over the square root of 4 pi squared plus delta squared. Natural log, so there's not a good way. Michael, that's a good question right there. You should always. So the way that so delta, so when you see those frequencies, right, I'm pretty sure they're on a log scale, if I'm not wrong. Michael?
I have no clue. I would assume so.
So that's why it's delta equals the natural log of the ratio between amplitudes. But the way that I think about it is it's just the distance. I believe it's just like the distance between those amplitudes. It has something to do with that. Just think about it as like how fast the oscillations are going down. Like our delta, our displacement. So how like the difference between amplitudes. Here's my first amplitude, my second amplitude, my third, and how that's going down. So the larger the delta, the larger the displacement, the bigger the change in amplitudes. That's the way that I think about it. Yeah. So definitely know this. Or, you don't have to memorize it because you can do this. This might be something that'd be good to do. You open up your test, the first thing you put down on your scratch paper or whatever is you're just deriving this real quick. And then that way you just have it at the top of your test and you can just kind of, go back to it, but it'll save you a lot of time if at least become familiar with it. So now we're going to go into the springs. This is all the easier stuff. Michael's going to get into the equations of motion and energy after this. So 2.62, we're going to write down the equations of motion and find the effective spring constant for the system shown right here. Pretty simple problem. Got a question for you guys though. If I went to go do equations of motion or energy method to, find my characteristic equation and find my natural frequency, yada, 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 can I use the energy method? There we go.
No.
Okay. Is gravity a restoring force?
No.
You got
No.
a damper.
There we go. All right. So the first thing we're going to do, I put it on there anyway. Yeah. So gravity is not a restoring force. The system's motion is along the vertical axis. So they end up canceling out. We're going to draw our, free body diagram. These are where my forces are going. My mass wants to go down. My spring and my damper want to pull back up. This is my SCP. Normally I put X. It makes my life easier. You could also use Y. Just, keep it consistent. Step 2, equation of motion. Newton's second law. We got mass times our acceleration, our displacement acceleration. This, right here, this means that my negative or like when I go down, that's my positive direction. I mean, that's kind of just the way that I think about it, where it's like, that's the direction of the motion. So that's positive in my head. You could also flip it, but the last answer, zeta is 0.00816. What was I saying? Oh yeah, so positive for this question would be down in my head. It's up to you, but but you know, the more you kind of stray away from the examples and the homework solutions, the harder it is to kind of make sure you're going on the same path, and it could lead to some issues. I mean, if you keep it consistent, that's great. It seems more complicated to me. So, but like I said, equation of motion, mass times our displacement acceleration equals negative c x dot minus k equivalent times x. And we're gonna just, you know, bring those over on the other side, set it equal to 0. Now, what I don't know is my k equivalent, right? It's in series. So step 3, I'm going to just kind of go through the whole, I'm not going to go through the parallel one, and I'm not going to go through the damper proof or whatever, but it might just be kind of easier for you guys to see why the spring series equation is the way that it is. Because I know that it's really hard for me to remember that stuff from like electrical, because you know, you have like inductors and capacitors and resistors, and now we got springs we're talking about, and dampers, and things in parallel versus series. They flip flop all the time, and it's kind of hard to like keep your head, you know, kind of remember all of that stuff. So I'm just going to kind of go through it. So we have our initial length 1 and our initial length 2. We have our K1 and K2. Our final, we have these two forces, right? Created by the springs. Still have our spring constants. But now our length is L1 plus, ooh, that should be an X1 right there. Sorry about that. L1 plus X1. So that's our displacement. And same thing on the bottom, L2 plus X2. So our force 1 is equal to K1 times X1. Our force 2 is equal to K2 times X2. You know, this is the spring equation. Then we're going to set those, we're going to derive an expression for X. So put that, divide by the spring constant. X1 equals F1 over K1, sorry. Same thing with X2. And then we're going to go and look at the displacement. So the equivalent displacement is going to be just X1 plus X2. So the displacement of this whole thing, the delta X, is going to be the delta X of this one plus the delta X of this one. So X1 plus X2. Force of the spring, we know is K times X. We can also say that that's K equivalent times X equivalent of the whole thing. And the force of the spring is equal to F, to the force here, F1, and it's also equal to force 2, the one down here. It's because of Newton's third law, every force is equal and opposite. So our K equivalent equals the force of the spring over X equivalent. So from now on, I'm just going to refer to the force as the force of the spring. We're going to plug all that good stuff in for our X equivalent. So right here, I'm taking my X1, which is force 1 over K1, plugging that into the equation. And I'm inputting the Newton's third law into there. So I'm taking away the force 1 and the force 2, and I'm just saying that it's the force of the spring. Taking that out of the denominator, they cancel, and I end up with K equivalent equals 1 over K1 plus 1 over K2. And then if I wanted to, I can put that back into my equation of motion. So, I mean, you know, yeah, you know, and you could go further with this as well, you know, K1 times K2 over K1 plus K2. Yeah, both the same equation. You know, you're not going to be asked to do this proof on the test. It's just something, it's a good, you know, now that you've seen it, you might be able to know it right off the top of your bat, even though it's on the formula sheet. Just a good way to conceptualize springs in series versus parallel. Determine the effective stiffness of the springs shown in this figure. So now I'm just going to go straight to the formula sheet. We got these equations right here: springs in series versus springs in parallel. This is some easy stuff. We all did this in EE. So the first thing we're going to do, parallel K1 plus K2. So now, you know, if we knew these values. Oh, and this is going to definitely be a good easy question that, you know, it might be just like kind of a give me, would be, it's definitely good if she does give you a spring problem, which is I would say likely. It would be a lot more complicated than this. You know, there might be 2 or 3 over here and then they all connect, but it's, you know, we've done this countless times before, especially in electrical. So just kind of go over it, just do a couple problems, get some practice in. Step 2, series. So now, you know, we got our K in parallel and our K3, and we have our springs in parallel formula. We're going to input all of our values here. So what am I doing here? So I'm taking my K3, right? I'm taking my K3 and I'm multiplying K3 over K3, 1. And over here, I'm doing the K1 plus K2 over K1 plus K2, just to try to get my denominator down, my denominator of the denominator to be the same. So then I can use some algebra there. Yep, same, they're the same denominator, move to numerator, bring that up, and we have K equivalent equals K3 times K1 plus K2 over K1 plus K2 plus K3. And, you know, should go back, you know, if you do put something like this, if that's like your final answer, I'm pretty sure the GTAs will take it, because that's who's grading the test, is the GTAs and Dr. Powell. Pray for this problem. Yeah, it's I would say likely that you get a spring problem. This would be kind of like one of the give me's. If she's being nice, she'll give you a spring problem, but it will be more complicated. So I definitely do some practice. The first equivalent solution, I mean, it is the same equation. It just doesn't look pretty. She might, I mean, it'll say it in the question. It's still technically the same equation. You still got there. Yeah. But that being said, this equation here, that's for a really, really simple system. And when you start having K5s and they're in, you know, series, and you have, you know, 3 or 4 different arguments down here on the denominator, you know, it helps to, you know, when you're doing the series stuff and you're solving them one by one, it definitely helps to get to this point, get a value and keep going forward. And I'm pretty sure you might want to get some practice with using, I feel like she might give you the values for the K constants. So you might not even have to box this or this. You'll just have a number. Yeah, do we have to simplify it that much? I mean, it's like I said, these are the same equation. It's kind of up to you. Obviously, this looks a little bit prettier. But if you feel like it's going to screw up your answer, I think you'll be okay with this. But like I said, I'm pretty sure you'll be given the like constant values. So you'll have a number. I think that's, if I'm remembering correctly, that's kind of what my test was. How important are units? Like, very important. But just remember, all right, so yeah, units are important with springs and dampers, especially going forward. You know, if for this test, you're going to want to know it because, if you're given, we've only done problems with variables. We haven't with this, right? With the springs. But when you're solving for a spring constant, and that's got to be your answer, you're going to have to put units on your paper, or you're going to get it wrong, or, maybe some points off. We've all had to kind of live with that. But going forward with the new material after this test, it makes your life a lot easier when you know what goes where. But it would be if you just look at the equation of motion, the C value goes right next to the x dot, or the velocity. So that's newtons over seconds, if I'm remembering correctly. And then our K is newtons over meters. No, I'm sorry. Dampers is newtons over meters over seconds. It's going to be uploaded. Yeah, we're going to try to upload it. We're 100% going to upload the PowerPoint. Yeah, the file is going to be massive. We're going to 100% upload the PowerPoint. And if for some reason we can't get it up, if we can't get the recording uploaded, we will try. We're going to have a Q&A tonight at 8. So if you have any more questions, feel free to pop in. All right, keep going here. Oh, problem 242. I think this is Michael's turn. You want to take it away?
Yep, I'll request access again. All right, cool. So 242, this is one of those equations where you'll have to look at it and you're gonna have to take a couple things from it. Firstly, the easiest thing, can we use energy methods? I also can't. Oh,
No.
and then secondly, is gravity a restoring force? And
Why isn't gravity a restoring force?
good
Because
question.
you could kind of say that this is a pendulum, right?
That is true. You could say that.
No, really. Gravity is not bringing it back to equilibrium.
There you go. Yep.
Yep, there it is. All right, cool.
Yeah,
And
because
even
a lot of people would see that and think pendulum and just work with gravity.
that is true. And another thing that might confuse people is if you were to displace this upward, gravity would kind of look like it'd be a restoring force. However, the thing is going to oscillate around the center. So in the bottom position is equally as important as in the top position. In the bottom position, gravity isn't restoring it. So it's not a restoring force. But now that we've established that, we can move on and we can set up our equation of motion. It's asking, should mention that. Yes, it is. It asks for the natural frequency of damped oscillation. So omega d, that's what it's asking for. And then it also asks for the critical damping coefficient. So to start, we'll set up our equation of motion. We'll want our rotational linear relationship because the spring will deflect at y and the damper y dot, and we'll have to set up those relations. And once we have that, I believe we can go ahead and take them.
Oh, shit. I'm trying to write in the chat. Am I screwing you up?
I don't think so. I think that might have just been me clicking twice.
Okay. Sorry, I'll just stop touching everything.
I do have a quick question. So in a problem like this where we have a rod revolving around a point, are we immediately going to use angular displacement over, like, I guess, Cartesian?
Yes.
Now that also depends on the problem though, because some might ask you to put it in terms of x dot. If they tell you to put it in terms of x dot, then no, you'll have to write your rotational equation in terms of x dot. You see, when I did this, I was like, gravity is not restoring. And then I looked at it and I was like, oh, it is. So I just dropped it. So that's my mistake. But yeah, you shouldn't put that there. I dropped it in the next equation. But yeah, so you take your moment around that origin point, and then our next step would be to compare that to our characteristic equation. So we want to get it in terms of the characteristic equation. And what you'll find is if you do this, if you write this in terms of x dot or theta dot, you should get the same. You should get the same answer, like when comparing them to the characteristic equation.
Wait, I'm just gonna touch on the coordinate system thing again.
Yep.
It shouldn't matter. You should still be able to get the same thing in the end. You should be all right. If you solve this equation using Cartesian, it's gonna be a lot harder. But if you do it correctly and then you compare it to the to if we just used polar coordinates, it would work out to be the same, but it's just going to be a lot harder. So you know, when I see something going through an angle, going through theta, that's when you just in your mind polar. But if it's like dropping, you know, if it's translational, you're gonna want to go with the Cartesian.
Yeah, and so the equation we're working with is that second equation that equals 0. That's the equation we're working with. And then we can, so we'll compare it to our characteristic equation and we can get our natural frequency, but we can't stop there because they asked for natural frequency. We will use our natural frequency, we'll calculate zeta, and we'll combine both of those in the damped natural frequency equation to solve for damped natural frequency. And yes, the review session will be posted later. A and B are squared because, so when you set up your rotational system, you know that y dot will be a sine theta. We don't account for gravity. I forgot to take it out. That's my bad. It's not in that second equation. But so the reason they're squared is you'll take y dot equals a sine theta, and because of small angle assumption, it's a theta dot. You'll plug, so you'll have cy dot times a. That'll get you a squared. Similarly, you'll have the same thing for b.
Yeah, we're ignoring gravity here. He screwed up. We all make accidents.
We ignore gravity because it's not a restoring force in the system, in that when you displace the system, gravity does not restore the system to equilibrium.
So what the way that I think of you know the restoring force, and I know that that's a really weird concept, but if you do set up your free body diagram and all your forces correctly, it should end up canceling, but not in this case because you know. But the way that I think of restoring force is, all right, if we think of a pendulum, gravity is taking that through the rotation and it's adding a horizontal component, a tangential component to it. And the SCP is going to be along that vertical axis and it's restoring it back to here, right? Whereas with this problem, our SCP is horizontal and our gravities end up canceling out. All right, hold on. We got a quick question.
Yeah. So again, we can set up y dot as a sine theta dot. Is that what you have right there?
Yes.
So that means the vertical velocity would equal to a times sine of the angular velocity.
Yes.
All right.
Yes. So the reason we're doing that there is we're just we're just we're going to polar coordinates. That's the whole reason for that. Why don't we consider gravity for vertical bars? For vertical bars, what do you mean? Vertical bar, like a mass with a spring?
Why do we?
Yeah, okay. So that's because there's no horizontal component to it. Because all right, if I have a mass here and it's connected to, let's say, like a roof, and I got a spring in between and it's bouncing up and down, there's no gravity isn't adding anything this way. My SCP is down here, right? It's where my block started.
It might help to go back to that one slide where I drew the picture of it. too,
Yeah, you want to do that?
just really quickly. Just for the last time. The one below it.
So here's why it cancels. Yeah, you should go over this one more time.
So quickly, one more time for everybody who missed it, we have restoring force. Gravity takes you away from the static equilibrium position. It does not return you back, so we'll ignore it. And in any case where that happens, we'll ignore it. And then we go to, and you'll see how the math cancels in cases where, are we good? Yeah, you'll see how the math cancels in cases where your gravity does not restore you back to your static equilibrium position. In the case of vertical bars, we have a component of gravity that brings you towards the static equilibrium position. So in that case, you'd include it.
Yeah, and if you guys still have an issue with this, we can talk about it more at the end.
Mm-hmm. Can you fast travel me back? All right, cool.
Hey, I got a question real fast, if it's okay.
Yeah, what's going on?
Let's say we're given a problem like that pendulum, and it doesn't tell us which way the deflection is. Do we just assume one way or the other, and then just make the moment positive to that direction?
Yeah.
Talking about an example.
No, not this one. Like a
Oh,
pendulum
are you
problem.
saying like the pendulum I drew?
Yeah.
In any one of these problems, that's personal preference.
Yeah.
So just take whichever one you like.
So the SCP though, it will be. So think about like if you let it go, where is it going to end up? And the SCP is going to be here. But you know, if you're starting it over here on the right side versus starting it over on the left.
Yeah. I mean, like we're given it as a SCP, and then we have to assume which way it deflects.
Yeah, I mean,
Okay.
it should end up being the same as long as your coordinate system, like your positive versus negative direction. You know, as long as they're consistent, it should work out. Also,
okay, perfect, thanks.
Yeah, actually, I don't have anything. All right.
Do I have control again? Okay, cool. All right. So I think we left off at, you solve for natural frequency using, comparing it to the characteristic equation. You can then use natural frequency to solve for zeta by comparing it to the other part of the characteristic equation. And then with zeta and natural frequency, we can use the damped natural frequency equation, omega n times the square root of 1 minus zeta squared. And then we can solve for the damped natural frequency. So does anybody have any questions on that one?
I've got a question.
What's up?
So if this was a critically damped case, would that C just become C critical?
Yeah, and zeta would be 1 in that case.
Cool.
Yep.
Actually, I believe that's the next step. Yeah. Mm-hmm. So if they ask you to find critical damping, you plug in CC for C, zeta will be 1, and then you can solve for the critical damping coefficient. Cool. So I think I'm gonna move on to next problem.
Can you go back
From-
can you go back a slide?
Oh,
Copying.
yes.
Yeah, the hardest
yeah, I
part is
forgot we
definitely
didn't
setting up
scroll.
the initial equations of motion. You know, if your free body diagram's incorrect, it screws up everything. So that's why I said, you know, if you don't want to go through all of the, you know, because these problems do take a long time to do, but a good way to practice and be time efficient is if you could just go through a whole bunch of them, setting up the free body diagram and getting the equation of motion. It'll take you 5 minutes, and you can just go through a bunch of them and make sure you get that down.
All right, it looks like Bryson's good. Do you
Yeah,
also
you're good.
need? Do you also need this slide? Oh, I guess we'll post them. I'll just
Yeah,
I'll
okay.
move
You
them on.
reposted it. Just keep going.
Cool. All right. So problem 32. There's this one was from your homework, and you could do this the energy method way. So the energy method way, I'm gonna move through pretty fast because you did it through your homework. But you can also do it using equations of motion. But for the energy methods, so you're going to look at all your sources of kinetic energy. You have two disks kind of moving around, and then you have a mass. One of these disks is a point mass, and one of these disks is just a rotating mass. And then you have another point mass that's just moving like this. So the trick here is you'll have to know that this rotating mass is a point mass. If they give it to you as a mass, how do we know what is causing motion and what is receiving
That's a good
motion?
question.
Well, so sometimes they'll just give it to you. Sometimes they'll say that this is X dot moving to the left.
That's what we're given here. You see
There's
that
other
there's an
times.
arrow right there that says X dot. That's where we're kind of starting from.
Mhm.
Or you know, sometimes you're given wherever the SCP is, you'll have like an SCP with like an arrow. That's like the direction it's moving in.
Kyra, I will get to your question. That's kind of the point. I'll get to your question later.
Yeah.
And like when you're determining what is receiving motion, what's causing motion, I mean, they're all linked. They're all linked. So if one moves, they're all going to move. It's a 1 degree of freedom system. So it doesn't really matter what's like receiving the motion. If you move one piece of them, they're all going to move.
But it does matter what direction.
Yeah. If they give you
But
a direction,
you'll be given a direction.
Mhm.
For a problem like this, yeah, we'll get to that. We'll show you.
Okay.
Yes and no is the answer.
The cylinder would have to be already rotating, or the spring stretched since the rope can't push the wheel into turning.
We don't necessarily know that that's a rope. It could be something metal, so it could be turning that going left anyway.
If you move that point mass, the system moves.
Yeah,
Just
so don't think of
simple
it
as
as a rope with tension and all of that. Just think of it as so that connector between the cylinder and the mass. If the mass moves, so does the cylinder. Don't think too deep into it.
I think when I get to the equations of motion one, it'll kind of explain the forces behind it, but we'll get through this one really quick. So you have your rotating mass moving that just has one kinetic energy, so it's 1/2 J1 theta dot 1 squared. You have your regular point mass moving, so that's just 1/2 MO X dot squared. And then you have your rotating point mass. This thing is going to have two kinetic energies, 1/2 M2 X dot squared and 1/2 J2 theta dot squared. That should be a theta dot. But once you've set that up,
Michael, why are we doing for the cylinders? Why are we doing both rotational and translational?
Because so the first cylinder is not translating at all. It's isolated. It's not on the ground. It can't rotate and move. The second cylinder has makes contact with the ground, so there'll be friction for it to roll. And while it rolls, it will also have a mass that's moving at a velocity. So that's why you'd have to add both components. Are the x dots equivalent? Yes, these two x dots are equivalent. Since if this point mass moves at x dot, the point mass next to it should move at x dot. And then we can go ahead and set up our relations here. So for the first rotating disk, theta dot is attached. Your x is attached to the r1, so you know theta dot 1 is x dot divided by r1. And the second point mass, you're attached to r2. So that's how you relate everything in terms of x dot. And then your final equation for this, for kinetic energy, would be this. For potential energy, we're going to want to look at the two components of our system that store potential energy. You have a spring towards the bottom, and you have a spring towards the top. Now that first spring, since there's no rotational motion, it's just kx squared. That second spring is related by, the x is related by radius 1, and the x2 is related by the big radius. So you'll have to solve for x2, plug that in, and then you can get your potential energy. And then we're going to combine the two. So we're going to bring back our kinetic energy, and then we can use conservation of energy. The change in kinetic plus the change in potential equals 0. So we'll take the derivatives of these really quickly. You'll know that using chain rule that you'll bring the 2 down, and then you'll also multiply by the derivative of the thing you took the derivative of. And that's what we get here. And then we can combine. And we can combine, you know that the change in kinetic plus the change in potential equals 0. They both have an x dot term that cancels. And then you have this in terms of your characteristic equation. You can have your natural frequency is just k effective divided by m effective. Any questions there? That's pretty standard. And now we're going to run through it using the equations of motion. So this is going to get a little bit more complicated because we're going to have, I'll explain up the individual systems. So the first disk, you'll have a spring. So with your initial displacement to the left, you'll have a spring resisting it to the right. And this force 1 between the two objects is kind of the string resisting movement, and that's your equal and opposite force. This is what drives the movement of the system, at least between these two. So you'll have that force 1 acting on both the first disk and the first point mass, but then you have another situation where you break it into the two forces, and you'll have a force 2 resisting motion of the point mass, as well as another force 2 pulling this rotating point mass. And whenever you have rotation, you'll have friction in the same direction. That's from dynamics. So now with this jumbled mess, we can write an equation of motion for each of the systems. The first system, you have F1, R1. The second system, you have F1 and F2. And then the third system, you have F2 and the force of friction. Now we have 3 equations, 3 unknowns. We have to get rid of F to be able to solve for F1 and F2. So how we do that is we take a, it does suck. We take a moment around the center to get something in terms of the force of friction. You plug that in, and then you can plug it in here. What is the potential energy? We'll get there as well. The F values, no, those F values, you don't really know what those are. Those are just the two forces that link the motion. Because if you displace this mass,
Give it as like a bar.
yeah, if you displace the mass,
keep
you're
going.
going to have a force on the disk, as well as a force resisting the motion of the point mass. So we don't necessarily know what those are. Our goal is to eliminate those. Friction is always in the direction of rolling, because that's how you get your net
Yes.
force.
Right.
Yeah. Cool. So yeah, this all kind of simplifies down. We can solve for F1, and once we solve for the force of friction, we can solve for F2, and then we're going to plug those into this equation, and that will kind of unite all our three systems. So was that supposed to happen? Okay, yeah, no. So when we combine everything, we get something like this. And we can further simplify it down using our equations for theta dot double dot 1 and theta double dot 2. And we bring it down here. And then you could just, that's our final. Yeah, that's our final. You have your natural frequency equals K effective divided by mass effective. And you can solve it this way. Now, moral of the story is don't do it this way, ever.
Yes.
If you have the
But-
option to use energy methods, use energy methods.
Yeah. But you get the same answer, but don't do it. I mean, you can if you want to check your answer or something like that. But do we have an equation for what?
No, they just give you J. They just give you J as J. That's it.
Yeah. So if the question doesn't explicitly say it in the problem, like use energy method or use EOM, first just pray that there's not a damper in it, because then you can use energy method.
Yeah. Now you might feel like I wasted your time there, but there's a point. There's a point to this. So now we look at problem 55. Energy. You're going to go and do this energy method because we said energy method was easy. It works. But can we do that? If they say that the disk is J, they put a J next to the disk, that is your moment of inertia. That's just it. J is I.
Assumption for J meaning the polar moment of inertia.
Like, let me go back to that. Oh. So if you see this problem and they attach a J as a property of the disk, that's your moment of inertia. You don't need an equation for it. That's just it. If they don't give you a J, then you're going to be looking at, oh, what's my moment of inertia? It's a disk. It's 1/2 mL squared. But if they give you that J, it's just J. That's just their way of saying, this is the moment of inertia. Don't plug in an equation for it.
She might even give you a value for it too,
Mhm.
just a number for it.
Yeah. So back to, yeah, so we lose energy to the damper. We can't use energy method. So we're stuck in this one doing the equation of motion. And you'll see some similar things going on here. You'll have a force between the two masses, force between the rotating disk and the mass. And then you'll have a friction force because you're making contact with the ground. And you'll have to do a similar deal here. So you'll set up the point mass equation of motion, pretty easy. Just words are hard. You do minus F equals minus C x dot minus K1x. And that's your equation there. For the rotating one, it's going to be a little bit more complicated. Did I do the rotating one? Oh, I mean, I guess this is literally it here.
What'd you do here? Go back.
Did I?
Oh, okay.
I think I forgot one step. Well, I forgot to put in one step there. But essentially what we do there is we take the moment around a moment around the friction force. So then we can get the moment in terms of F and Kx too. So you would see
When
that.
we post these, we'll add that step in.
Yeah, I actually have the PDF where I did it. I'll just have the PDF of all those problems uploaded. But yeah, you take the moment there, so when you take the moment at the friction force, your K2 X2 would be at a distance A plus R. Does everybody see that? Okay, yep, cool. And then to take the moment around from the force, it'll just be F times R. Cool. And then we move that to here, and you'll see that's kind of what we did. You did K2 A plus R squared. And then we plugged in our F here times R equals IA theta double dot. And then from there, we'll simplify, we'll plug everything in, and we'll try to get it down to our characteristic equation. We'll move everything to one side. And then we'll have our effective damping as well as our effective spring costs in there. And then we can compare that to our characteristic equation, and we'd be able to solve for the natural frequency as well as zeta.
Can you go back real quick to the last slide?
How come we didn't create a radius group? So we actually did when actually no, we didn't need to do it because I believe we just put everything in terms of theta. Did I not? Oh, no, we put everything in terms of x. So we took that theta double dot, and theta double dot, you see with any displacement would just be theta divided by r. Or sorry, x divided by r. So we set up our relation down here. A, they give you A to B, that distance from the origin to the ground, I believe. My mouse is gone? Wait, is it back? Okay, cool. So we use the radius relation
Yes.
in polar coordinate. You will use the radius relation every time you need to, every time you either need to relate, every time you have a rotational motion in a 1 degree of freedom system, you'll have to use some sort of radius relation. Because what'll happen is you'll have some terms in terms of theta dot and some terms in terms of x dot. You'll need them both to be in the same, you'll need them both to be like terms. So when we come here, we put everything in terms of x dot.
So to kind of tap onto that, so even if you're not in polar coordinates, even if you're trying to get your whole system in Cartesian,
I think that's
you're still gonna need the
everything
polar
there.
coordinate
Do we have
relation.
any more questions on this problem? A plus R. So I think we can get a better picture of this problem for you because that's one of the dimensions. Give me 1 second.
Kevin, no, I think you have
I
muted
cannot.
me. Yeah, I think you did.
I accidentally just, I couldn't hear anything you said.
Yeah, bro, dude, I've been talking to myself the entire time.
Really?
Yeah, man. But no, she will not. I do not believe that she will clarify. That's something that you kind of have to figure out.
Chapter 2 problems. Cool. All right. I'm gonna. Would I be able to override and share my screen? Let me.
Yeah, I'm just gonna stop sharing. There you go.
All right. So you see this problem here? They give you that distance A is the distance from the origin to the spring, right? So that would be why you have R plus A there. Yeah, when I drew my arrows there, I kind of covered it up, but in short, that's why that happens.
Do you want to pull up your PDF of it? I mean, now's pretty much the point where this is the end of it. This is the end of all of our examples. So, you know, if you have any questions, anything like that, feel free to unmute yourself or raise your hand, or we'll probably be on for the next 30 minutes or so. So
Hey, I have a question.
what's going on?
So yeah, back to just what I had asked about whether she would clarify if it's supposed to be in terms of x or theta. How would we go about deciding which term we should write?
It's a good question. All right, so if the motion, the way that I think about it is if the motion, the movement is angular, if we have angular velocities, I'm talking about the initial. So in this case, our initial would be the block moving translationally, correct? But if we have a pendulum or just a cylinder and like that's given the initial, I believe that you'd probably be better off using polar coordinates. But when there's blocks moving left and right or up and down, I like to work in Cartesian. So if there's a cylinder there, it's a lot easier to you know, just pop it into Cartesian. Makes your life easier.
Okay, thanks.
Like for this one, when I chose which one I wanted to do, I said, oh, I have 2 theta terms versus converting 3 x terms. So I just converted the 2 theta terms.
Okay. All right, thank you.
Hey, I have a question.
What's
Yep.
up?
Okay, what is the best way to prepare for the exam? Like what should be my plan? Like for
Homework.
this afternoon, tonight, look over the homework,
Oh yeah.
go over the homework.
Oh yeah. That's a big wink wink right there. Like she's very, very fair with her tests. She, you know, they're going to be, I mean, if you know the homework and you know you've gone through the lecture examples, you know, you might not need to go through every single lecture example and do it 3 or 4 times, but if you've seen it and you know how it works and you know the concepts, but I would know the homeworks like the back of my hand. And if you do that, you're gonna get an A.
And what about this review? Should I go over this review again? Because I didn't catch everything. Just sitting here taking notes. So
I mean, these are hard problems. We purposely chose hard problems, especially not in the beginning, not when I was going through it, but the end problems. We tried to choose the hard questions because when you get to the test, you know, you might be pleasantly surprised.
all right, thanks.
But I mean, if you know how to do these, you'll be fine.
All right, thank you.
Do not worry about anything like homework problem 6. That question was kind of unreasonable. Don't worry about that one.
Okay, thank you.
Oh, and Laplace transforms, you don't need to worry about that. I don't believe so. I think that's next exam.
I mean, the next 2 exams are just different. Like, controls is something else. That's like the next exam after that one. But the one before that is just vibrations in a different way.
Yeah,
So like,
the next exam is just adding on to this. I would say same difficulty. I think the second test for me was easier. However, the final, the control stuff, that's where we all need to buckle up.
So I have a question.
Uh,
The reason I asked before about which problems are best because I heard some, some comments that she likes the example problems.
mhm.
Now that you said homework problems.
Yeah, I studied. I spent most of my time on the homework problems, but there's only. I would focus more on homework 2 rather than homework 1.
Yeah, makes sense.
You get the EOMs and the energy. She's not going to ask you diff EQ questions.
We already took that class. So
yeah. You guys, you passed diff EQ if you're in here. It's not a math class, right? But I'm not saying don't go over the lecture problems. If I would do your best to be able to do both of them. But in my opinion, I think the homework questions are a little bit harder. So if you get those down, it's a lot easier if you know the hard questions. When you get an easy question, it's not that bad. If you want to really try to focus your time, go through the lecture examples and find the hardest problems you can. Because if you set yourself up like that and you get to the exam and the questions are really easy, then you did something.
Sometimes the example problems are in the homework. I noticed, I think for homework 1 they were repeated or is the same figure somehow.
So if that means they're really good questions, they're really important questions. So that makes, you should probably know those more than the others.
Perfect. Thank you so much.
You got it.
What'd you guys get on the first test?
I think you got like a 95, something like that.
Better question, what's the class average for the first exam?
I actually
class
don't know.
average
I think it was
80.
Yeah. I think it was a high B or a low A.
Oh shit. Okay, that's definitely a little more reassuring. Thank you guys.
Yeah. I mean, like I said, she's very, very fair with her exams. She's not looking out. She's not looking to fail anybody. She's as long as you know as long as you pay attention in class and know the homework and you can do all that, you should be fine.
I have no clue if she curved the class at the end because
I think she might have.
I think she might. It just, I don't remember. Can we go over 32 for the relations for X2? Was that?
Yeah, no nadir tests.
Yeah. This was that energy or equation of motion? Energy. Okay, yeah, for that one, it's just, you'll look at this one. I called this one theta dot 1, and you'll see that the string is attached to the smaller radius disk.
You want to zoom in a little bit?
Oh yes, I can do that. So you'll see that the string is attached to the smaller radius disk. So when you make a displacement on this disk, it'll be in terms of R1. And you know that X equals R theta. So we'd say X dot over R1 equals theta dot 1. Similarly, for theta dot 2, I came to this one and we looked at the displacement. The displacement here is just related to R2. There's no other complicated thing about it. Oh, you meant for the potential part? I think I draw that pretty well here. Okay, so I'm going to use these drawings to look at it. So to get down to, actually, I think I can draw. That will work better. So to get down to here, you'll have a displacement. We'll talk about this first displacement here. That'll be X divided by R1 equals theta. So we're cool with that. And you know that theta on this disk will equal theta on this disk because you can draw a line here. Yeah,
We're posting this.
You can draw that theta there. So theta on this disk and this disk are the same. So now we're going to come down here. We're calling this x1. That will equal x1 over r. To solve for x1, you then just multiply x by r, and you can say x1 equals r x over r1. For this problem, how did you know M2 was being translated as well as rotated?
Because it's on the ground.
Yeah, you see this, if it makes contact with the ground here, if it rolls, it will also be translated. Every application where you can use the energy equation, can you also use the translational? Yes, this method will always work. It's just obnoxious to do.
Yeah, that's kind of why we showed you how you could do it both ways. But if you can use energy method, do it.
Yeah, no slip. I mean, if you want it to be really technical, well, we say the mass doesn't have friction because of the rollers. Now, if you want it to be really technical, you could get the kinetic energy of the rollers. We're not doing that. They'll say the mass is no friction whatsoever, and the rollers are negligible, whereas this mass, this roller is not negligible because it has a mass. Does that kind of make sense? Yes, if K2 was a damper, you would have to do it this way.
And yeah, I'll make an announcement when we post it of where it is. I have to talk to Dr. Powell first, so I don't know yet.
She posts extra practice problem. I actually haven't seen those. Where are they?
Hello.
What's going on, man?
Yeah, no. So I know sometimes like before she begins the lectures, she would like put on the slide that, oh, like here are some extra practice problems that you guys could go over. I assume like those are like similar to the homeworks that you would give us.
Yeah. So like I said, if you have enough time, any practice is good. But the first thing that you should go over, the first thing that you should have down conceptually and mathematically, and going through all the dynamics, is the homework. I would say homework first, then lecture problems, then the practice problems. But the problems where they're repeated, where they're repeated in the lecture and in the homework, it's pretty obvious that she wants you to know those. It's pretty obvious that she thinks those are important questions. So if you don't just go through all of these problems without just kind of memorizing the steps, because if you understand like the mechanisms and the concepts behind it, that's where you'll really be able to succeed.
Yeah, it's like, if you were given this problem, can you draw your free body diagrams? Can you get your equation of motion? Alternatively, can you get your kinetic energy equations? Do you know how to set up your rotational and translational relationships? Any problems that help you practice these skills will be useful.
And if you're on a time crunch, and if you're pulling an all-nighter tonight, and you're kind of worried that you're not going to see it all, like I said, if first thing, I mean, I do the homework again, but if you're kind of on a time crunch, I would just kind of go through the harder questions and do the free body diagrams, set up your first line of equations, because we all know how to do algebra. Yeah, it might help if to solve it out, but if you can get the free body diagrams and the first line of equations of motion, that's the hardest part. After that, it's a lot of algebra. I mean, maybe a derivative here and there. YouTube, that's a good question. YouTube definitely comes in handy with the control stuff. I rely on that so much, but I haven't found any good YouTube videos. I mean, you go ahead, more power to you.
Who is Rebecca? Did you mean to do that?
Yeah, real quick. How long does she usually take to grade the exams and like release the grades?
Like a week.
Yeah, a week.
Okay, thank you.
Mm-hmm. So I and Jay, it's really just, if they don't give you it, I just wrote I in terms of whatever I took the moment around. If they did give you it, like in one of these, they give you that this moment is J1. You have to use that. They give you this moment of inertia is J2. You have to use that. So that's just J2, J1. You plug those in.
How many questions? Yeah, I'd say 3 to 5, 6 on the high end. But if she gives 6 questions, then a couple of those are going to be like the give me ones, like the spring problem. You can, like I said, we haven't seen the tests, but you can expect an energy problem and you can expect an EOM problem. Those 100%. All free response, yes.
I had no details about the percentage of people in each grade category.
Yeah.
I think somebody asked me to go over this equation of motion really quick, so I'll do that now that the part's here. So we drew this, we covered this, we had this in the slides. I mean, yeah, in the first slides. The thing we were missing was this moment equation, and we took our moment around the ground, right? Because we didn't want to deal with this friction force. So when we take our moment around the ground, you'll have K2 X2. Well, what is X2? When we look, X2 would be this distance right here, right? So we can solve for X2 being, X2 would be, did I do that right? I think I did that right. Yeah. So you have, so this length is A.
It's just weird because it's like you have your K2 X2 force really, it's drawn really close. But A is longer than that smaller radius.
Yeah.
Yeah, it's, if you look at the problem, it's like in the middle, it's like in the middle between the distance of like the small disc and the bigger one.
But yeah, so you have these two distances, A plus R. This distance won't change. So that's your hypotenuse. So A plus R sine of theta. You know that small angle, that's just theta. So now your new force is K2 A plus R theta. Now, when we're taking the moment, it's K2 A plus R theta times the distance from the ground, and that would be A plus R. So that's how you get that. And then the force is just a distance R away from the ground.
I got him.
Thanks. Real quick. So what happens to the sign there? X2 equals A plus R sine theta. I missed that. Sorry.
Small angle assumption. Cosine theta equals 1. Sine theta equals theta.
Okay. All right. Thanks.
Wow.
Yeah, and something like this, what I would do is I'd blow that trigonometry up real big, so I have, I can like kind of visualize it and I'm not all scrunched up. I mean, just kind of take your time with stuff like that. And like we said, we tried to choose hard questions, you know, because if you get this, if you get every step of this, I think you'll be fine.
Yeah, if you can do this, any equation of motion will be fine. Yep, no problem.
Like I said, I'll make an announcement. We'll probably be on Zoom for anybody who wants to drop by. If you have a quick question, and I'll make an announcement where we post this.
L theta. There's an L theta. I theta. Oh, that's just sum of the moments equals I theta dot, theta double dot. That's just your equation of motion. The
Yeah, so-
I, they didn't give it, so I just said the moment of inertia is I.
So yeah, if we're in Cartesian, it's
I
mass
tangent.
times x double dot, and then if we're in polar, it's I times theta double dot. It's just something.
I use I, J, interchangeable. Just
Well, J.
whatever they give you is what you use.
Yeah. And unless trying to think. So the polar stuff, the polar moment of inertia or the moment of inertia, you know, if she does ask you to find that, it'll be from one of the equations that's given on the formula sheet. Like I said, you know, she's not out for blood. She's pretty fair. Just kind of go over it, you know, 2 minutes, refresh your memory. But if I'm not mistaken, you might want to find one or two problems where you use numbers and you calculate it all out with the equations of motion. I don't know if the homework has any of those where you actually have given values.
Yeah, I'm not sure either, but I'll actually just pull up the formula sheet to make a.
Because I don't remember if she uses actual values or not.
I don't know. I vaguely, I'm not remembering.
I know she does. I mean, I know she does sometimes, but I don't know about the motion.
So if you were to use a moment of inertia and they didn't just give you J, it would be one of these. So like, don't worry about the notation too much.
And, you know, also keep in mind is like, this also isn't a solid mechanics class. You know, we're definitely more focused on the vibration aspect of everything, all the frequencies, natural frequencies. So, you know, if you do end up getting it wrong, it'll be just like a little part of the question, you know. She's pretty good about all that with partial points. Any other questions?
I think it's cool to stop the recording now.